Okay, let's unpack this. Today, we're embarking on a truly monumental deep dive.
It really is.
We're doing a foundational exploration of the core ideas that define the cognitive sciences. And we're drawing directly from a colossal alphabetical section of the MIT Encyclopedia of the Cognitive Sciences.
And this isn't just, a simple alphabetical list. It's more like an intellectual inventory. It really spans the full scope of how the mind works.
Yeah, and our sources are forcing us to jump disciplinary boundaries constantly, which is part of the fun.
Oh, absolutely.
Exactly. So our mission today is, I'll admit, highly ambitious. We want to distill these foundational, often super technical concepts, everything from how we feel pain to how radical rules get ranked and why a supercomputer plans its actions, and we want to get them into clear, high-value insights.
The goal is really to give you a cohesive mental map of this massive intellectual landscape.
In the clearest, most digestible way possible, even as the alphabet forces us to make these really sharp pivots.
And what's so fascinating here is how these entries, they just naturally cluster into these four critical domains. It just reflects the radically interdisciplinary nature of cognitive science.
So we're going to start with language and logic. This covers the deepest theoretical structure of human communication. We're talking about ideas like optimality theory and the crucial poverty of the stimulus argument.
Right, the argument which really defends the innate nature of grammar.
Then we're going to leap into the physicality of the body and brain. This is neuroscience, psychology, concepts like pain, the historical cartography of Wilder Penfield, the profound mystery of the phantom limb.
And the developmental stages, mapped by, of course, Jean Piaget.
And crucially, we've got the engines of thought, the computational and AI foundations.
These are the formal methods, the tools we use to model intelligence. So planning, pattern recognition, and even the rules of scientific inquiry itself, which we call parsimony.
And finally, we're going to engage with the deep structures of philosophy and representation. We'll be addressing the nature of reality and thought through physicalism, probability, and the concept of propositional attitudes.
We'll proceed entry by entry alphabetically. For each one, we'll give a clear definition, the core idea, and really get into why each term matters to the bigger picture of cognitive science, linking them conceptually wherever we can.
Let's start with O and jump right into the structure of human language with Optimality Theory, or OT. For anyone familiar with older linguistic models, this was a fundamental revolution in phonological and syntactic thinking.
Oh, it absolutely was. The older theories, the serial, process-oriented frameworks, they suggested that sound changes happened in these fixed steps, one after the other.
Like an assembly line.
Exactly like an assembly line.
Yeah.
If you change the order of the steps, you change the outcome. Optimality theory represents a huge shift to a system of parallel, viable constraint optimization.
Okay, that sounds really dense, but the core idea is actually quite elegant. So if the grammar isn't a factory assembly line with fixed steps, what's actually going on?
Well, the grammar is, instead, a massive parallel generator. So it creates all these possible output candidates.
Different ways to pronounce a word, for example.
Right. Different ways to pronounce a word based on the input structure. The actual realized form that you hear is the one candidate that best satisfies a ranked set of universal constraints.
So every candidate actually violates some constraint.
Yes, that's the key. Every candidate violates something, but the winning candidate is the one that minimizes the worst violations, all based on how that specific language ranks those constraints.
So as you said in the intro, it's literally a beauty contest for word candidates.
That's a great way to put it.
The constraints are like the judges, but the ranking, the specific hierarchy of those judges is what determines the winner. So a language might prioritize clarity over, say, ease of articulation, or the other way around, just by ranking the constraints differently.
Precisely. And the power of OT is in its unified scope. It's not just for phonology, it also works for syntax. In phonology, it's essential for explaining typological variation.
You mean why languages vary so wildly in their sound systems, their syllable structure, stress, tone, all of that?
Yes. Languages are essentially defined by how they have optimized this ranking system.
And this isn't just a linguistic theory, right? It has deep implications for the computational models of the brain.
Crucially, yes. OT addresses the learnability of grammars. So if the constraints themselves are universal and innate, language acquisition boils down to a single computational problem: learning the ranking.
So the kids just have to figure out the judge's hierarchy for their language.
That's it. And you can design algorithms to learn this specific ranking for a given language just by being exposed to positive examples. This draws these really fruitful theoretical connections to the optimization principles that are at the core of neural network models.
So it suggests that the brain might be performing a continuous parallel optimization process rather than just executing discrete serial rules one by one.
Exactly. It's a whole different way of thinking about computation in the brain.
Now for the first P entry, and this is the most visceral pivot imaginable, pain. We're moving from abstract constraints on sound to the physical, biological necessity of suffering. Among all sensory experiences, the sources really highlight that pain is utterly unique. Why do they make that distinction?
It's unique because of its exceptionally strong emotional or affective quality. When you experience pain, it's not just a sensation, it's inherently loaded with emotion. There's an urgency, a negative valence that touch or sight just don't usually have.
And so subjective.
Incredibly. Its perception is highly variable, influenced heavily by subjective factors. Your personal traits, your mood, your expectation. The threshold for pain varies drastically not just between people, but across your own body surface.
So let's delve into the physical basis, the nociception. How does the body register that initial noxious stimulus?
It involves two very distinct types of specialized receptors and two distinct sets of wiring. So first, you have mechanical nociceptors. These are highly specific. They respond only to very forceful mechanical energy that typically signals tissue damage.
And they use the fast lanes.
They use larger, lightly myelinated axons for transmission.
And the experience that's associated with those fast, lightly myelinated axons is?
That's the rapidly transmitted immediate and better localized pricking pain. It's that sharp sting you feel the absolute instant you step on something.
Okay, so that's type 1. What's the second type?
The second type is the polymodal nociceptor. These are much more general. They respond to noxious stimuli of many kinds, mechanical, chemical, and temperature. For example, they respond linearly to heat stimuli between 40 and 60 degrees Celsius.
And these use the smallest unmyelinated axons, the C axons.
Right, so the C fibers are the slow, poorly insulated wires that carry the sequel.
The sequel.
Exactly. The C fibers carry the poorly localized, delayed second or burning pain, the agony, the throbbing, that deep ache that sets in moments after the initial sharp sting.
And there's another crucial biological difference here, right? Hyperalgesia.
Yes. Unlike most other receptors that adapt and become less sensitive over time, nociceptors participate in hyperalgesia, which is a heightened response to subsequent noxious stimuli.
That heightened sensitivity you feel around an injury, that's hyperalgesia.
Yes. And there are two types. Primary hyperalgesia happens right at the injury site. It's caused by local chemical agents like bradykinin that directly stimulate the receptors. And this is critical for pharmacology.
Why is that?
Because other agents like prostaglandin E2 make the receptors more responsive. This is why common analgesics like aspirin or ibuprofen work. They inhibit those specific chemical agents.
And the second type?
Secondary hyperalgesia. This is strictly neural in origin. It possibly involves sensitization changes within the spinal cord itself, which extends the sensitive zone beyond the actual site of the injury.
Okay, so let's follow the signal up the central nervous system pathways.
Yeah.
The path for pain is fundamentally different from the path for, say, fine touch.
It is. Pain efferents enter the dorsal root of the spinal cord, and they cross immediately. Right there in the spinal cord. This is in sharp contrast to signals for fine touch and proprioception, which only crop much higher up in the medulla, closer to the brain.
And this anatomical difference has real consequences.
It's the reason that damage to one side of the spinal cord causes a loss of pain sensation on the opposite side of the body, but a loss of fine touch on the same side.
And this pathway convergence also explains the phenomenon of referred pain.
That's where cutaneous, so skin and visceral or organ nociceptors, converge as they ascend. The brain, which is accustomed to pain originating from the skin, misplaces the pain that's actually originating deep in the viscera to a peripheral site.
The classic example being the pain from a heart attack being felt in the arm or shoulder.
Exactly.
The sources also detail the body's own internal pharmacy, the built-in mechanism for pain control.
Yes, we have a descending pain control system. It involves the midbrain's periaqueductal gray, PEI, and the nucleus raphe magnus. These structures modulate pain intensity.
Oh.
They use interneurons that release opiate-like peptides called enkephaline's as neurotransmitters. This is our natural internal opioid system. The precise localization of pain happens in the somatosensory cortex, but the affective component, the anguish, the suffering, that's likely mediated by much more complex structures in the temporal and frontal lobes.
So the significance of this intense emotional reaction, this agony, is purely about survival, right?
Precisely. Extreme pain's emotional reaction is absolutely vital for survival. The rare clinical cases of patients who can perceive the stimulus but they lack that critical emotional reaction, they often die young.
Because they fail to avoid or stop doing things that are damaging their body.
Exactly. Both the sharp localized signal and the delayed effective response are essential for successful long-term survival strategies.
From the physical constraints necessary for survival, let's pivot back to the innate abstract constraints of language acquisition, specifically the parameter setting approach. This is a core idea within the study of grammar.
This model is rooted in Noam Chomsky's principles and parameters framework. The crucial starting point is the idea that linguistic knowledge, or I-language, isn't learned word by word or rule by rule.
Right.
Instead, it consists of universal principles that are shared by all languages, plus a finite set of innate switches or parameters with fixed settings.
So the incredible complexity of language acquisition is radically simplified. It's not about learning infinite rules. It's just about flipping a finite number of innate switches based on the specific linguistic input the child receives.
Exactly. The process is defined like this. You have the innate language faculty, which is S0, that has union set parameters. It gets exposed to primary linguistic data, PLD, which provides the triggers.
And the result?
The result is the final specific grammar, SF, where the parameters are now set. This framework offers a really powerful answer to the logical problem of language acquisition.
Which is how children can achieve this infinite competence from finite and often messy, incomplete input.
Yes. The innate structure severely restricts the possibilities from the get-go.
But pinning down the actual mechanism is difficult. The sources identify this as the trigger problem.
The problem is characterizing the parameters themselves. Are they tied to high-level structures, or are they localized to these things called functional heads or inflectional systems? And then, what specific forms or amounts of PLD serve as reliable triggers to flip those innate switches?
That's where the empirical work gets messy.
Very messy.
We have a concrete example provided here, though. The mechanism for morphological triggering and V-raising.
Right. So this proposal suggests that the richness of verbal inflection in a language acts as the physical, observable trigger for V-raising, which is just the displacement of the verb outside the verb phrase.
Okay, so in French, you see rich inflections, and the verb moves.
And in modern English, you see poor verbal inflection, and the verb defaults to V in situ. It stays within the VP. The idea is the child observes this rich morphological paradigm and just sets the V-raising parameter accordingly.
And the single mechanism links language acquisition to the evolution of language over time and even the creation of new languages.
That's the genius of the framework. Derek Bickerton's language bioprogram hypothesis suggests that creoles,
so languages that develop rapidly from really impoverished input, like pidgins.
Right, which are highly unreliable PLD. These creoles tend to manifest properties that correspond to the default, genetically specified, or unmarked values of the parameters.
So if the triggers aren't present in the input, the parameter just defaults to its initial, easiest setting. It's like a factory reset.
Exactly. When a Creole language forms, often stabilized by children who are exposed to unstable pidgin input, it's like we're observing the innate language faculty hitting the reset button and selecting the default options when reliable triggers are absent.
So it connects acquisition, creolization, and historical language change, reinforcing the idea that grammar is a recreation by each generation.
A fundamentally discontinuous process.
Yes.
And it strengthens that overall theme of the innate blueprint.
We transition now from the abstract rules governing human language to the abstract rules governing scientific inquiry itself. Parsimony and simplicity, or as we usually call it, Occam's razor.
Named after William of Ockham. And the principle is simple. Entities are not to be multiplied beyond necessity. This is absolutely foundational for all forms of induction, learning, and theory construction.
Not just in philosophy, but across computation and science.
All of it. And the sources break down Occam's razor into two specific, actionable aspects that are really relevant to cognitive modeling.
Okay, the first aspect relates to existence and proof. Observability or identifiability.
This means that any entities you postulate in a model have to make an observable difference. So in modeling data with equations, every theoretical parameter must be uniquely estimable. It has to be identifiable.
What happens if it's not?
If multiple sets of parameter values yield the exact same empirical result, then your model contains non-identifiable parameters that are, well, they're essentially postulated beyond necessity.
And the simple math example they give is perfect for illustrating this abstract point. If you model data with y dollars equals A plus B plus C, you can't uniquely solve for B and C individually.
You can only solve for their sum. And as we discussed earlier with optimality theory and its computational links, this isn't just a math exercise. It comes up constantly in practical cognitive models, especially in neural networks where the hidden layer connection weights aren't directly observable.
Right, so they can often be swapped or changed without altering the input-output mapping.
Exactly.
The second, and often more controversial aspect, is minimization. So minimizing the number of postulated entities, which is typically measured by the number of adjustable parameters in a model.
And this immediately leads to the central computational challenge in all of science, the trade-off problem. Since a more complex Model 1 that has more adjustable parameters will always fit the training data better, how do we justify that extra complexity? How much better does the fit have to be to say, yes, we need that extra parameter?
That is the motivation driving almost all the statistical criteria we use today.
Absolutely. Standard significance testing and criteria like AIC, BIC, and MDL. They are all mathematically rigorous attempts to manage this fundamental trade-off.
Yeah.
They impose penalties for complexity.
To make sure we only select a more complex hypothesis if the empirical gain truly warrants the extra parameters.
All right.
It's important to realize, though, that this definition of simplicity, just counting the parameters, has its limits.
It does. It fails to capture more philosophical ideas of simplicity, like the difference between a simple straight line curve and a highly wiggly curve that has the same number of parameters, or, the kind of profound simplicity you get through unification under a fundamental principle.
Right. Those broader, almost aesthetic notions of simplicity are just notoriously difficult to quantify and trade off against empirical fit. The concept of simplicity and optimization leads us directly into a core domain of AI, pattern recognition and feed-forward networks. These networks are essentially functional descriptions of how we believe intelligence should work in a machine.
Right. So a feed-forward network is a graphical representation of a parametric function. It consists of input, output, and these crucial hidden vertices or nodes.
And they're connected by weighted edges that correspond to the adaptive parameters, the weights and biases.
Exactly. And the goal is to use a training set of example solutions to infer the underlying regularity so the system can successfully generalize to solve new, unseen problem instances, like identifying a face or a fingerprint.
The learning process here is all driven by minimizing error.
You define an error function, say the squared difference between the network's prediction and the desired outcome, and then you minimize that error by adjusting those thousands of weights and biases using a gradient-based optimization algorithm.
What was the critical moment in the 1980s that allowed neural networks to evolve from simple single-layer models like perceptrons into the powerful deep networks we know today?
The breakthrough was the ability to calculate the required adjustments efficiently. Researchers replaced the older non-differentiable threshold activation function with a differentiable nonlinearity.
And this allowed for the use of...
This, crucially, allowed for the use of backpropagation, which is an efficient technique for calculating the derivatives of the error function backward through the network, allowing adjustments to weights across multiple hidden layers at the same time.
So backpropagation is the computational mechanism that allows a mistake at the very end of the process to efficiently tell every single internal node exactly how much it was responsible for that mistake.
That's a perfect way to put it. This mechanism allows for efficient training. And modern research tends to view this training from a statistical perspective.
Meaning?
Meaning that training a network is basically modeling the probability distribution of the target data conditioned on the inputs, which is an application of the principle of maximum likelihood.
But the perennial challenge, and this ties right back to parsimony, is generalization.
The central challenge is always ensuring performance on unseen data. A network that is too large or too complex relative to the data, it risks overfitting.
It memorizes the noise instead of extracting the useful underlying regularity.
Exactly. And this is addressed by limiting complexity, formalized through models like Bayesian learning or the minimum description length MDL approach, which mathematically formalizes the exact trade-off we just discussed under parsimony.
Shifting now to the physical brain, let's discuss Wilder Penfield, 1891 to 1976, a monumental figure who literally mapped the functional landscape of the human cortex.
Penfield was a pioneer neurosurgeon and the founder of the Montreal Neurological Institute, or MNI, and his lasting contribution wasn't just surgery, it was integrating patient treatment with multidisciplinary brain research.
His revolutionary technique, the Montreal procedure, it sounds like something straight out of science fiction.
It was an incredible innovation. It was used to guide epileptic surgery. To make sure he didn't damage critical functional areas, Penfield systematically mapped the brain's properties by applying brief, low-voltage electrical stimulation directly to the cortical surface.
Of fully conscious patients.
Fully conscious patients, yes.
And the resulting map changed neuroscience forever.
Oh, yes. His mapping revealed two key principles. First, he established the somatotopic organization of the primary motor and somatosensory cortexes,
which is a precise, point-to-point topographical relationship between areas of the cortex and specific parts of the body.
Right.
Which gave us that famous, almost mythical image. The sensory and motor homunculi.
Those stylized cartoons, the distorted human figure draped over the cortex showing how the hands and lips have this massive disproportionate representation compared to, say, the torso. Penfield also confirmed cerebral asymmetry and hemispheric specialization by mapping language zones, Broca, Wernicke, and the supplementary speech zone, all predominantly localized in the left hemisphere.
And stimulating these zones would literally interfere with or arrest the patient's ability to speak.
Just stop them mid-sentence.
He also stumbled upon the physical basis of memory and emotion during these procedures.
This happened during temporal lobe stimulation. Patients would sometimes report the awakening of these incredibly vivid, long-lost memories, sometimes involving emotion, sometimes simple sounds. This confirmed that the medial temporal region, which includes the hippocampus, is crucial for human memory and emotion.
And later in his career,
he even proposed the centroencephalic system in the upper brainstem as the seat of higher integration. He conceptualized consciousness as impulses passing through circuits between the brainstem and cortex,
which foreshadowed later theories stressing the importance of the midbrain reticular formation.
Exactly. He was way ahead of his time.
From Penfield's static adult brain maps, let's look at how that system develops in infants. Perceptual development research thoroughly overturned William James's classic idea of the infant's world as a blooming, buzzing confusion.
Oh, that view is historically important, but it's factually incorrect. Modern research using these clever methods like preferential looking and operant conditioning demonstrates that infants have surprisingly impressive discriminatory and anticipatory abilities right from birth.
Their perceptual system is anything but chaotic.
Far from it.
The sources outline 5 key findings about this process. The first is that perception is prospective, or forward-looking.
Yes, meaning infants anticipate the consequences of events. They'll show defensive blinking in response to a visually illuminating object, for example, but not to an object that's moving away.
They're predicting a collision and initiating a defensive action.
They are.
The second finding emphasizes the central role of motion in defining reality.
Motion is fundamental because it reveals the constant properties of objects, their unity, their size, shape, substance, that are otherwise hidden.
Right. So, for example, a 4-month-old infant only perceives the unity of a partly occluded object if it is actively moving behind the occluder.
And motion is also key to detecting biological motion, like recognizing a walking human figure just from a few illuminated spots on the joints.
Right. It's an incredibly powerful cue.
Third, multimodal unity. Perception isn't learned one sense at a time.
No. Perception is unified from the earliest moments. Infants orient to sounds, and they can match the sounds and visible motions of faces and voices by 5 months old. Exploration itself is naturally multimodal, integrating information from touch haptic cues and sight.
Like differentiating rigidity or elasticity through mouthing or handling.
Exactly.
The remaining 2 findings directly connect the developing perceptual system to the body's action systems.
Key finding number 4, layout and action. Distance and layout are perceived in units of body scale and integrated with motor skills. This means that as infants transition from crawling to novice walking, they have to relearn how to detect relevant information.
Like avoiding steep slopes. Because their motor control and balance have fundamentally changed. This is brilliantly demonstrated in the moving room experiments, where changing visual flow patterns can actually cause novice walkers to fall over.
because their perception is integrated with their less stable motor skills.
Yes.
And the fifth finding concerns the perception of the self.
Infants perceive the self as a unit that's distinct from the world and capable of control. They can differentiate their own ongoing movements from novel movements, which confirms that the self is perceived as distinct and controlling.
Which ties neatly into our next P entry, reinforcing the power of the brain's internal self-map.
It does.
The phantom limb phenomenon is arguably the most powerful piece of evidence that our body image, our self-map, is hardwired and independent of the physical reality of the body.
It's a profound and nearly universal neurological illusion. It's experienced by 95 to 100% of amputees. The phantom is felt as tingling, having a definite shape, and initially moving normally in space,
though it may later telescope or fade into the stump. What's truly remarkable is the extent of this phenomenon. Amputation isn't even necessary to experience it.
That's the crucial insight that proves a central mechanism. Phantoms occur after severe nerve damage, like brachial plexus avulsion, after spinal or anesthetic blocks.
You can get phantom legs or a phantom body.
You can, and critically, in paraplegics with complete spinal breaks, who report a phantom body, sometimes including visceral sensations, even sexual feelings and orgasms.
So this confirms the strong presence of a central pattern-generating mechanism, or an innate neural blueprint for the body schema that is highly resistant to peripheral damage.
Yes.
The subjective experience of the phantom must be utterly convincing.
Oh, it feels perfectly real, and it's reinforced by pre-amputation details. Patients will report feeling a tight ring on a missing finger or a painful bunion that existed before the foot was removed.
Wow.
There are even reports of phantoms of internal viscera, the bladder, the rectum feeling full, leading patients to report attempting to urinate or pass gas despite the missing parts.
How does the phantom integrate with the sense of self?
The phantom is perceived as an integral, moving part of one's self, even if it's experienced in a bizarre position, like dangling in midair.
And the sources confirm this link by citing the converse condition, somatoparaphrenia.
Right, where a patient with a right parietal lesion denies that a body part belongs to the self. This demonstrates that our sense of bodily integrity relies on specific, localized brain mechanisms that, when damaged, can produce the exact opposite illusion.
And the ultimate evidence for the innate blueprint theme is found in children born without limbs?
Yes. Approximately 20% of children born with a congenital limb deficiency still feel a phantom of the missing part. This is incredibly powerful evidence that the neural blueprint of the body is innate, preformed, and independent of external sensory input.
Though experience like fitting a prosthesis can later influence the phantom's perceived shape.
It can, but the blueprint is there from the start.
Let's turn our attention back to the linguistic domain, starting with phonetics, the science of the physical events of speech. It's vital to distinguish this from the abstract symbolic system of phonology.
Right. Phonetics is the scientific study of the physical aspects of speech events. It deals entirely with measurable properties. It's highly interdisciplinary. It involves physics, biology, psychology.
Whereas phonology, which we will cover next, is the grammar component dealing with symbolic categories.
Exactly.
So phonetics is typically broken down into three subfields, describing the stages of a sound's life.
First, speech production. This describes how speech is physically made. The airstream mechanism, phonation.
Sort of vibrating vocal cords, the primary sound source.
Right. Then articulation, which is modifying that sound source using the vocal tract, and the oronasal process. This subfield provides the basis for descriptive systems like the International Phonetic Alphabet, IPA.
Okay, second, acoustics, focusing on the transmitted sound wave.
Acoustics describes properties like frequency and duration. The core principle here is the source filter theory. The acoustic sources, phonation and noise, are modified by the filtering function of the vocal tract, your mouth, throat, nose, which generates specific resonances called formants.
And analyzing the frequencies of these formants is a key measure used to distinguish different vowels.
It is.
And third, perception, which is basically the reverse engineering of speech.
Experimental phonetics uses lab equipment, like the sound spectrograph, to detail acoustic and perceptually relevant properties, such as voice onset time, VOT,
which is the duration between releasing a stop consonant like P or B and the onset of vocal cord vibration.
Correct. And then theoretical phonetics uses this precise data to propose physical constraints that limit and influence the abstract rules of phonology and historical sound changes.
So now we step up one level of abstraction to phonological rules and processes. These are the mechanisms that describe how a single word can have different pronunciations depending on its grammatical or prosodic context, like the consonant alternation between atom and atomic.
These are the unconscious rules that native speakers just effortlessly apply, and they fall into two main categories. First, local sound change phenomena.
This includes assimilation.
Right, where sounds become more alike. For example, the prefix in becomes in before a bilabial consonant in impossible.
Okay.
Then you have dissimilation, where they become more distinct. Deletion, like the reduction of unstressed vowels to schwa. And insertion, like the aspiration of the tit in athomic.
The second category relates to rhythm and grouping.
That's prosodic grouping. This involves organizing phonemes into syllables, which often requires inserting a schwa to break up an impossible cluster, and then organizing syllables into rhythmic units called metrical feet.
Strong-weak or trochaic versus weak-strong or iambic.
Correct. And we see this pattern in how longer names are predictably shortened into nicknames, adhering to a specific foot structure, like Elizabeth shortening to the trochaic Lisa.
It sounds like these processes are driven by a constant balancing act between being clear and being efficient.
Exactly. They are phonetically motivated. They either enhance perceptibility in strong contexts, or they minimize articulation in weak contexts or fast tempos.
It's the great compromise of the speech apparatus.
It is.
And the sources introduce two fascinating terms to discuss the limits of these rules. Myopia versus blocking.
Phonological processes are often myopic, meaning solving one phonetic problem can inadvertently create another. For instance, London ush deletion reduces effort, but it creates awkward vowel clusters where none existed before.
But they are generally not self-defeating and will block if the output of the rule isn't an improvement.
Exactly. If liquid dissimilation were to turn floral into florar, the rule would block because that change doesn't make the articulation or perception any better.
So if phonetics is the physical event and phonological rules are the processes, what exactly is phonology?
Phonology is the grammar component itself. It determines a language's basic sound units, the phonemes, and their permissible combination patterns. It's the abstract symbolic structure underlying all of speech.
The structural components are highly structured, hierarchical, starting at the lowest level.
At the lowest level, we have distinctive features like coronality or labiality. These define the phonemes, which are the small set of basic sequential units.
And those vary wildly from just 11 sounds up to 141 across different languages.
They do, and their order is crucial for meaning. These phonemes are then grouped via syllabification, which is constrained by language-specific rules, like requiring a vowel in every syllable.
And above the segmental level, we have the features that stretch across entire phrases.
Those are the suprasegmentals: stress, tone, and intonation. Tone, like in Cantonese, is used to distinguish individual words. Stress and intonation in languages like English distinguish word types, like convict versus convict or sentence focus.
This symbolic system, however, introduces a fundamental mismatch between the abstract representation and the physical output.
This mismatch is created by those phonological rules and processes we just talked about. They introduce a significant gap between the mentally represented phone sequence and its phonetic realization.
Which is why words like fields and feels can sometimes merge in actual pronunciation, making the speech signal an imperfect cue for the listener.
Exactly.
So if the output is dysfunctional from the hearer's perspective, why does this complexity even exist?
It's rooted in conflicting constraints. The complexity arises because the system is constrained both by the brain, which favors hierarchical grouping, and the speech apparatus, which favors simplified, effortless articulation.
In modern theory, recognizing the limitations of serial rules has moved toward nonlinear and constraint-based approaches,
Culminating in Optimality Theory.
The acquisition process for this complex sound structure, phonology, acquisition of, begins before the first word is ever spoken, emphasizing that perception always precedes production.
That's because the auditory system matures much earlier. The Inatus theory posits a language acquisition device, a LAD, and parameter setting. Newborns are just astonishingly capable.
They are.
They can discriminate all possible language sounds, making them linguistic universalists from day one.
So the key developmental event is not learning new sounds, but unlearning sounds the child won't need.
Exactly. Around 10 months, infants undergo a perceptual reorganization. They lose the ability to discriminate sounds that are not distinctive in their native language. And this is consistent with the neurological theory of learning by selection.
Where the environment selects which innate distinctions to keep, and it prunes the unused ones.
Right.
This early capacity is then used to solve the fundamental problem of hearing continuous speech. segmentation?
That's bootstrapping. To segment the continuous stream of input into words, infants use prosodic cues, stress, and constituent edges in a process called prosodic bootstrapping.
And this prosody may even help set initial syntactic parameters like word order early on.
Yes, long before the child has acquired a large lexicon, it links the sound system directly to the grammar.
What about physical production?
Babbling starts around 6 months as the vocal apparatus approaches the adult state, and crucially, the acquisition of suprasegmental's rhythm and intonation precedes the acquisition of segments, which supports the idea that the overall structure is acquired first.
And the universal first syllable is CV, consonant vowel.
Because it maximizes the difference in sonority, which is the simplest and easiest structure to produce.
And the constraint on all of this is time.
We observe a clear critical period. First language, or L1, acquisition is impaired after age 5, and the acquisition of the phonetic realization of a second language, L2, what leads to a foreign accent, is impaired after puberty, suggesting a biological window for tuning the physical speech mechanisms.
So let's link the linguistic theory back to the brain structure, the neural basis of phonology. How does this complexity map onto the left hemisphere dominance for language?
Well, we rely on studies of adult aphasics and neuroimaging in normal subjects. We can divide production into selection, planning, and articulatory implementation. What's often surprising is that high-level selection and planning errors are not neatly localized.
Meaning aphasics, regardless of whether they have anterior, Broca's damage, or posterior, Wernicke's damage, show similar types of errors.
Correct. Both types show deficits in selection, saying Keems for teams, and planning swapping sounds like rough beef for roast beef. These errors reflect statistical tendencies involving phonetic feature changes, but they lack a distinct, neat neural locus.
Which implies that high-level planning is highly distributed across the brain.
It seems to be.
However, the physical execution of the sounds is localized.
Yes. Articulatory implementation deficits, which relate to the timing and coordination of muscle movements, like producing an overaspirated teat or difficulty coordinating syllables that involves the left inferior frontal gyrus, including Broca's area, the precentral gyrus, and the basal ganglia.
And crucially, these deficits only emerge from left brain damage, confirming the unilateral specialization for the motor control of speech.
That's right.
What about perception turning sound into meaning?
Perception is highly complex. It involves both anterior and posterior brain areas. And while most aphasics show discrimination deficits, the data suggests these relate more to the quantity of errors rather than an impairment in the basic patterns of phonological structure.
So the underlying phonological structure may be intact, but the ability to access or utilize it in a rapid, reliable way is what's impaired.
That seems to be the case.
Now we make the sharpest pivot of all, moving from the structure of sound to the structure of reality, with the philosophical bedrock of cognitive science. Physicalism. Ontologically, what does this doctrine claim?
It is the doctrine that everything existing in spacetime is a physical thing, either a basic particle or an aggregate of particles. It is the fundamental denial of non-material entities, like Cartesian souls or spirits.
If something exists, it exists as matter or energy defined by physics.
That's the core idea.
But the real difficulty in cognitive science is the property problem. How do psychological properties, like consciousness or belief, fit into this physical picture?
Precisely. If we take physical properties broadly, to include computational, chemical, and biological ones, physicalists split into two main camps. First, reductive physicalism. This camp claims that higher-level properties are reducible to physical ones. For example, the mind-brain identity theory states that the psychological state of pain is nothing more than the physical event of C-fiber stimulation.
But that identity theory struggles against the multiple realization problem, the idea that pain can happen in different physical substrates. And that leads to non-reductive physicalism, or property dualism.
This is the position that psychological properties are an irreducible autonomous domain, even if they depend entirely on the physical. Within this camp, you have emergentism,
which suggests that properties like consciousness appear when physical conditions are right. But they are genuinely new, inexplicable properties with distinct causal powers.
Right. The correlation between the brain state and the subjective state is simply brute.
The other major non-reductive form is functionalism.
Functionalism defines psychological kinds by their causal roles, what they do, rather than what they're made of. This allows for multiple realization.
Meaning, the function of desire for food can be instantiated in human neurons, Martian goo, or silicon chips, as long as the inputs lead to the same outputs.
Right. And since the psychological property isn't tied to a specific physical substance, it's considered irreducible.
Despite these deep internal divisions, all physicalists share one core commitment that links mind and body.
That is mind-body supervenience. The psychological character of a system is entirely fixed by its total physical nature. There can be no change in a mental state without a corresponding change in the physical state.
Identical physical conditions yield identical mental phenomena.
Always.
But this commitment creates a severe conceptual headache, which the sources call the autonomy conflict.
Right. If physical laws fixed all causal facts, why can't we explain everything physically? Non-reductive physicalists argue that determination, the physical facts fixing the mental facts, is not the same as explanation.
So physical facts may determine the emergence of subjective experience, but they can't explain why pain, and not happiness, emerges when those C fibers fire.
Exactly. They argue the explanation requires reference to this autonomous, irreducible psychological domain.
Following up on the fundamental nature of the mind, let's discuss Jean Piaget, the intellectual giant, who translated these huge philosophical questions about human knowledge into empirical psychological ones.
Piaget saw intelligence as a continuation of biological adaptation, a sort of cognitive organ. His work established constructivism, which positioned him midway between pure realism, where knowledge exists independently, and nominalism, where knowledge is mere convention.
So for Piaget, knowledge is built up by the individual through active interaction with the environment.
It is.
His central and lasting contribution was charting the developmental sequence, defined by functional continuity but structural discontinuities, the famous stages.
This sequence is marked by the progressive abstraction of conservation. It starts simply with object permanence.
Knowing an object exists even when you can't see it.
Right. And it culminates in the mastery of abstract laws of physics and logic. To achieve this, a child has to learn to conceive of space as a structured entity, a container that forms a mathematical group of displacements.
What, according to Piaget, drives this construction process forward from one stage to the next?
Two mechanisms: novelty, the emergence of genuinely new knowledge that couldn't have been derived from the previous stage, and necessity, the interconnection of existing knowledge into logically necessary systems.
And the fact that genuine novelty emerges was Piaget's strongest evidence against both pure nativism and pure environmentalism.
Yes, because the knowledge wasn't there initially, but the environment doesn't contain the necessary logical structure either.
And the abstract principle guiding all this growth.
Equilibration. Piaget considered this the necessary developmental principle that subsumes both nature and nurture. It results in the continuous, endless optimization of the living system, which he called homeostasis.
So he saw his famous stage models as merely contingent algorithms.
Right. His core epistemological claim was that this principle of equilibration is what drives the system toward necessary logical structures.
Here's a fascinating detour that ties cognitive modeling back to culture: pictorial art and vision. The source suggests that art reveals the brain's shortcuts and economies, encoding vision.
Art exploits the non-verticality of representation. Artists achieve powerful 3D illusions by using impossible colors or inconsistent shading, and in doing so, they show us exactly where the visual system relies on efficient, simple processing rules, rather than a perfect, objective reconstruction of reality.
The power of a simple line drawing is the prime example of this shortcut.
Absolutely. Line drawings convincingly convey 3D structure, yet lines do not exist in the real world. Occlusions are just brightness or texture changes.
And the fact that this effectiveness is universally observed in infants, monkeys, and people from diverse cultures suggests that lines may directly activate a sparse internal code for object structure in the brain.
Right. The brain has found this economical way to represent the essential structure of an object without needing to process all the physical detail.
And the brain is surprisingly tolerant of large-scale distortions in pictures.
That's the evidence for viewpoint invariance. Pictures are flat 2D projections, but as we move our heads or walk around them, the depicted objects maintain their perceived shape over a wide range of viewpoints.
If our internal representations were true Euclidean 3D models, moving about the picture would cause grotesque distortions.
And since that doesn't happen, it is prime evidence that our internal representations of 3D objects are not perfect Euclidean models. They follow a different, simpler geometry that favors stable shape perception.
Finally, the observation about inconsistent lighting.
Artists routinely use shading and shadows that are physically inconsistent with a single light source, yet observers rarely notice this flaw. This shows we don't globally reconstruct the light source for the entire scene. Instead, we detect depth cues locally, taking advantage of the natural redundancy of information in the real world. We're optimized for speed and efficiency, which allows local inconsistencies to just slip past.
We must pause now to discuss one of the most tragic and seminal figures in the history of AI, Walter Pitts. His short life and brilliant work laid the philosophical foundation for neural networks.
Pitts was a legendary logician and an autodidact who, late in his life, systematically destroyed virtually all traces of his own existence.
But his foundational work, co-authored with Warren McCulloch in 1943, was titled A Logical Calculus of the Ideas Immanent in Nervous Activity.
That paper is a seminal text.
What was its core concept? Bridging logic and neuroscience.
It was directly inspired by Leibniz's dictum that any unambiguous task can be done by a logical machine, and also by Turing's work. Pitts and McCulloch formally interpreted the neuron, acting as a pulsatile device, as the element of a logical machine.
This provided the first formal mathematical foundation for how neural activity could realize complex logical functions.
It did.
They later extended this idea to perception.
Yes. Their 1947 work, How We Know Universals, attempted to interpret the cortex as a net that could abstract form independent of scale or position.
A radical early attempt to explain how we recognize a chair, whether it's tiny and far away or large and close up.
A very radical attempt.
Tragically, his career ended abruptly and dramatically.
His association with McCulloch and the vibrant MIT research group was severed abruptly in 1952. Norbert Wiener, who had become a mentor and father figure to Pitts, broke ties due to manipulative actions by a third party.
And the emotional devastation led Pitts to lose all initiative.
He abandoned his work, he destroyed his notes, and he died alone, having effectively erased himself from the historical record long before his physical death. His influence, however, remains indelible in the study of computation and mind.
Moving back to the computational domain, let's analyze planning. This is the core cognitive process in AI and humans, generating a representation of future behavior to constrain or control that behavior.
Early AI focused on domain-independent systems. The most influential was the General Problem Solver, or GPS, of 1959.
And that introduced means-ends analysis.
A powerful heuristic. It involves detecting the difference between the current state and the goal state and selecting operators, or actions, to remove those differences, setting sub-goals if necessary.
Then came strips, which formalized the action space using logic.
Strips use first-order logic to represent domain states and defined actions. Strips operators via clear preconditions, a delete list, which is what the action removes, and an add list, what the action adds. It searched through the application state space or situations by simulating the consequences of actions.
But the crucial shift in modern planning was moving away from linear sequences to partially defined plans.
This shift allows for least commitment planning, postponing decisions until absolutely necessary. Partially ordered planning, POP algorithms, represent plans as partial orders on actions rather than fixed linear sequences.
Which requires complex protection mechanisms to ensure that preconditions remain satisfied even when actions are executed in parallel.
Right, like the modal truth criterion.
And the most practical modern approach integrates hierarchy to manage complexity.
That's the hierarchical task network, HTN planning. It uses a library of actions with hierarchical decomposition, moving from high-level goals, like build house, down to detailed primitive steps, like hammer nail.
It supports refinement planning.
It does. And recent research has also focused heavily on addressing environments of uncertainty, incorporating conditional branches and modeling planning problems as Markov decision processes, where outcomes are inherently probabilistic.
Shifting sharply back to language, let's explore polysynthetic languages. These are the languages that challenge our notions of word boundaries, allowing the spontaneous formation of extremely long, complex words, often equivalent to an entire English sentence.
Languages like Mohawk, for example. Their extreme structural reliance on morphology over syntax makes them critical testing grounds for linguistic universals.
Because if a principle holds true in analytic languages like English and in highly synthetic languages like Mohawk, then that constraint must be innate to the human language faculty.
Exactly.
What's the common feature that builds these complex words?
Noun incorporation, where the noun referring to the affected object is expressed inside the verb. And the striking universal finding is that both English noun compounding and Mohawk incorporation prohibit incorporating a noun referring to the cause of an event.
Which supports the universal that affected objects form tighter constructions with verbs than causers do, regardless of how morphologically complex the surface word is. Polysynthetic languages are often described as having free word order. They are non-configurational. Does this challenge the idea of universal syntax?
Well, it seems to on the surface, but the insight is structural similarity at a deeper level. Since the verb often contains elements indicating the person, number, and gender of both the subject and object, noun phrases can be omitted or appear in virtually any order.
So what's the crucial finding?
The crucial finding is that these elements in the verb are functionally equivalent to pronouns in languages like English. The abstract structure, who did what to whom, is maintained, suggesting deep, universal structural constraints despite the surface differences.
Let's move to the philosophical foundation of meaning. Possible world semantics. This theory is essential for logical reasoning about things that are not actual.
This approach rests on the truth-conditional theory of meaning. So to know the meaning of a sentence is to know the conditions under which it would be true. Possible worlds capture these truth conditions beyond the single actual world.
And this gives us the tools to define fundamental modal concepts with logical precision.
Precisely. Necessity is defined as a proposition being true in all possible worlds. Possibility is being true in at least one possible world.
And this framework is necessary for logic, because it allows us to talk about things that don't exist.
Right. For instance, the conditions under which the sentence "I am seeking a unicorn" is true, even though unicorns don't exist in this world.
Implementation requires assigning values to sentence components based on multiple contexts.
Yes, values are assigned based on semantic indices, which include worlds, times, speakers, and domains. This is typically done through logical form. And philosophically, the approach is neutral on whether these other possible worlds are metaphysically real or just linguistic descriptions.
So for cognitive science, the focus is on providing the logical structure for the categorization of representational content, independent of how that content is physically stored in the mind.
Yes, that's the key.
The poverty of the stimulus argument is perhaps the most famous and fiercely debated argument for the innate blueprint of the human language faculty. It frames language acquisition as an immense computational paradox.
It applies the philosophical concept of the underdetermination of theory by data to language learning. The child hears only a finite set of example sentences, finite data, yet must acquire a grammar capable of producing and understanding an infinite number of sentences.
And critically, that finite input data is compatible with an infinite number of possible grammars.
An infinite number.
So how does the argument resolve this paradox and lead to the conclusion of innateness?
The conclusion is that some fundamental aspect of grammar must be innate because children rapidly and uniformly acquire language and they converge on one specific grammar.
Right.
They do not make many logically possible errors that the input data does not explicitly exclude. Their innate faculty guides them away from the infinite set of wrong choices.
Can you elaborate on the key evidence that supports this claim, that children constrain their errors innately?
The most famous example is structure dependence in question formation. When you're forming a complex yes-no question like, is the dog that is running happy? Children never mistakenly move the first "is" they encounter.
They know, implicitly and without being taught, that the movement depends on the structural relationship between the words, not just the linear sequence.
And the input data, in isolation, does not explicitly teach this constraint, yet children adhere to it systematically.
There's another fantastic example from Peter Gordon's compounding research.
Yes, he showed that children systematically distinguish between irregular plurals, which are allowed in compounds like mice eater, and regular plurals, which are excluded, like rats eater.
And since plurals are rare inside compounds in the input, a general learning device shouldn't acquire this distinction easily.
Right. The systematic adherence demonstrates an innate constraint guiding the learner toward one grammar over all the others.
And this argument is directed even at sophisticated learning models, like connectionism.
Indeed. The argument is that even connectionist models, which challenge the nativist view, have to be designed with innate architectural constraints on what they can learn and how they process information.
So they might provide a different mechanism for learning, but they don't obviate the need for innate design features necessary to restrict the infinite hypotheses generated by the impoverished input stimulus.
That's the argument.
Now we move to the crucial interface between language and context.
Yeah.
Pragmatics. This is the study of context-dependent aspects of meaning that are abstracted away from the strict logical form of a sentence.
The goal of pragmatics is to characterize how features of the speech context determine the actual proposition expressed. We're moving beyond the inherent meaning of words, which is semantics, to what the words are used to do in a social interaction.
One key subdomain deals with shifters, words whose referent changes constantly.
That's deixis, or indexicality. These are shifters like I, here, now, and tense markers. Their meaning is constant, I always means the speaker, but their referent varies entirely depending on the context of utterance.
Then there are speech acts, which focus on the speaker's intention.
This domain distinguishes the propositional content of an utterance from its illocutionary force, the speaker's intention, like an assertion, a promise, a request.
And this explains indirect speech acts, such as phrasing a request, "Can you pass the salt?" as a question about ability.
It does.
Pragmatics is also essential for understanding presupposition.
A pragmatic presupposition is a restriction placed on the common ground, the shared beliefs between the speaker and the hearer. If that shared belief fails, the utterance is inappropriate or infelicitous, not strictly untrue.
And the choice of words for reference is a purely pragmatic decision.
When a speaker chooses between using a proper name, a full description, or a pronoun, that choice depends entirely on the assumed information status of the referent, whether the hearer is assumed to know the referent or whether the item has been mentioned recently.
Finally, information structure uses syntax to aid comprehension.
This is how syntactic constructions, like the passive voice or cleft sentences, are used to package information to facilitate incorporation into the hearer's knowledge model. The speaker marks hearer new content as focus, ensuring the listener integrates the novel information correctly and efficiently.
Let's focus on presupposition itself, given its role in filtering information. It is conventionally conveyed content that is treated as old information.
Right. And the classical diagnostic test for presupposition is that the content is retained under the application of major logical operators, negation, interrogation, and conditional assumption.
So if I negate the sentence, Marty has a bicycle too, the underlying belief that someone else has a bicycle remains true.
It remains.
What are the common linguistic features that trigger this old information filter?
The triggers include factive predicates like regret, which presupposes the truth of its complement, adverbials like only or even possessive case, and syntactic constructions like pseudoclefs.
What happens when the shared context doesn't contain the presupposed information?
That's failure. The utterance is infelicitous. However, in a cooperative interaction, the addressee may accommodate the speaker by assuming the truth of the presupposed content after the fact, thereby saving the conversation.
This is frequently used by gossips who employ factive verbs to introduce news while pretending it was already mutual knowledge.
All the time.
The theoretical challenge associated with combining these elements is the projection problem.
This asks how the presuppositions of the parts of a complex sentence combine to form the presuppositions of the whole, and operators are classified based on their effect.
So you have holes,
like negation or questions, which pass the presupposition straight through. You have plugs, like the verb say, which block it entirely. And you have filters, like believe or conditional constructions, which pass it along only under certain conditions.
For instance, the conditional sentence, if Marcy sold her bicycle, then she regrets selling it, acts as a filter.
And it cancels the presupposition that Marcia sold her bicycle for the whole utterance.
Let's turn to primate cognition, exploring whether the intense social life of primates exerted extraordinary evolutionary pressure on their brains, leading to complex tracking of relationships.
This field largely investigates three problems to measure cognitive capacity. Problem one is imitation.
Okay.
While tool use is observed, acquisition is slow in the wild. However, apes reared in high information, human environments do show advanced imitation.
Which suggests the fundamental capacity exists but requires a special environment for its emancipation or release.
You'd seem so.
Problem two is the depth of abstract concepts.
Primates show remarkable skills here. Trained chimpanzees grasp primary count principles, and even untrained rhesus monkeys and tamarins spontaneously perform simple arithmetic addition and subtraction using expectancy violation procedures.
They can also access concepts like transitivity and cause-effect.
They can.
But the most crucial test is mental state attribution, or theory of mind, Tom. The ability to understand that seeing provides a window into knowledge.
And the evidence remains weak for a fully developed Tom. Apes will follow eye gaze, but they fail the critical test. They do not understand that seeing provides a window into knowledge.
They don't consistently alter their behavior based on what another individual believes or knows.
Right, which strongly suggests they lack the capacity for a fully realized theory of mind. And that is a major distinction between human and non-human primate cognition.
Continuing with our closest relatives, let's explore primate language. The curiosity here is immense, given the DNA similarity and the discovery of a human-like Wernicke's area homologue in the chimpanzee brain.
Early projects focused heavily on production teaching apes sign language like Washoe or symbolic tokens like Sarah, but researchers realized the assumption that production implied comprehension was flawed.
Apes could produce symbols without truly grasping the underlying semantics at a human level.
Exactly.
This led to a crucial shift in focus towards semantics and comprehension.
And this shift was successful. Apes learned lexicograms for abstract categories and could use them to label objects they could feel but not see. This is the essence of semantics, representing things not necessarily present.
The most compelling case is Kanzi, the bonobo.
Kanzi spontaneously learned word lexicograms and even novel human speech just by observation alone, having been reared in a language-rich milieu. His skills were then quantitatively tested against a 2.5-year-old human child named Elia on 415 novel requests.
Things like, take the gorilla to the bedroom.
Exactly.
And the result was astonishing, emphasizing comprehension over production.
Both Kanzi and Elia performed similarly, around 70% correct. This demonstrated that Kanzi's comprehension skills vastly outpaced his production skills.
So the conclusion is that elementary language competence is possible in apes.
If they are reared from birth in a social communicative context that prioritizes comprehension, linking this competence to the evolutionary selection for complex brains.
We return to logic and how we form judgments about likelihoods with probabilistic reasoning. We have to start with the normative approach, the mathematical ideal standard.
Right. Normative reasoning, constrained by Kolmogorov's axioms, requires two things. First, judgments must be coherent, meaning they satisfy the axioms and avoid guaranteed losses or Dutch books. Second, they must be well calibrated.
Meaning the stated probability, like 80% likelihood, must match the actual long-run outcome frequency.
It has to.
But the descriptive reality is that human reasoning often deviates significantly from this ideal standard.
We rely on intuitive judgment heuristics. The most famous is the representativeness heuristic, evaluating likelihood based on resemblance A resembles B rather than crucial statistical factors like prior odds or base rates or sample sizes.
So people focus on how well a description fits a stereotype, ignoring the low prior probability of that stereotype existing in the general population.
I do consistently.
Support theory deals with how the structure of the question itself biases judgment.
It shows that probability judgments focus on the strength of evidence, or support. Simply unpacking an event into its components increases its perceived likelihood because different descriptions yield different judgments of support.
And when complex inputs have to be weighed, the human judge often proves inconsistent.
Human judges are notoriously poor at weighting and combining attributes consistently. Linear models that simply capture the judge's past decisions, this is called bootstrapping, often outperform the judge himself.
Because they apply the judge's own insights more consistently, without interference from momentary variability or over-reliance on singular factors.
That's right. The machine is a better version of you.
To understand that reasoning, we need to understand the bedrock interpretation of likelihood itself, the foundations of probability. Here, the core is the degree of belief interpretation, or the Bayesian view.
In the Bayesian view, probability is a numerical measure of degree of belief in a proposition, and it is always conditional on evidence, so PAI.
This means unconditioned probability statements, like the probability is X, are meaningless unless the underlying evidence is stated.
Correct. And this framework provides a rational basis for making decisions under uncertainty. It basically resolves Hume's problem of induction.
What are the key consequences of this conditional view of belief?
First, assertions conditioned on different evidence are not contradictory. Second, while a degree of subjectivity exists, since people have different initial experiences and evidence, objectivity is achieved through intersubjective agreement once evidence is shared.
And third, the idea of the objective probability or propensity is misleading.
All probabilities are conditional. Even the 50% probability of a coin toss is conditional on the coin being normal.
This leads to Bayesian inference.
This is the dynamic process of updating a prior probability, or your initial belief, to a posterior probability given new evidence. Priors can be assigned using weak assumptions like the principle of indifference or maximum entropy.
And the great strength is that data quickly swamps these weak initial prior probabilities,
leading to convergence among different observers once evidence is shared.
This view contrasts with the frequentist interpretation.
The frequentist defines probability as long-run frequency, which struggles to address singular, unique events, like the probability of a first rocket launch. The Bayesian view, using degrees of belief and hypothetical evidence, handles singular events easily.
And while the debate is largely academic, when abundant frequency evidence exists as they converge.
The Bayesian approach proves more broadly applicable for reasoning under uncertainty and decision-making.
Problem solving is fundamentally defined as transforming a given situation into a desired goal situation. In cognitive science, this is conceptualized using the problem space.
Right. The problem space is the branching tree of achievable situations that are generated by applying operators or actions. And since problem spaces are often immensely vast, think 10-toe states and chess solving a problem becomes a matter of highly selective searching using heuristic rules.
And the most powerful general heuristic is means-ends analysis.
This involves detecting the difference between the current state and the goal state, and selecting operators to remove those differences, setting sub-goals if necessary. This strategy is central to early problem solvers like GPS, and it remains fundamental to both human and AI problem solving.
Problems are classified based on how defined they are.
Well-structured problems have sharply defined situations, operators, and success tests, like linear programming. Ill-structured problems are vaguely defined. Success tests are complex, and solutions are often satisfactory rather than strictly optimal.
Like designing buildings. In ill-structured domains, the way you represent the problem is often the solution itself.
That's a huge part of it.
How do experts, whether they're architects or chess masters, manage these massive spaces efficiently?
Expertise depends on heuristic search combined with recognition. Experts recognize cues that access thousands of chunks of specialized knowledge from memory. This recognition process accounts for much of what we call intuition and inspiration in experts.
And modern trends focus on integrating learning with problem solving, often using parallel, connectionist models and unified cognitive architectures.
Like Newell's SOAR system.
A mechanism central to modeling how the brain executes sequential actions in AI and cognitive psychology is the production system. What are these formal systems?
Production systems are computer languages like OPS5, and they're used to model cognitive processes entirely based on condition action rules called productions, or non-array-arrow.
They essentially state, if conditions in memory are satisfied, then take the specified actions.
That's it.
The power of these systems is significant, as the rules themselves have the full power of a Turing machine. How do they interact with memory?
The conditions specify properties that must exist in working memory, so active short-term or semantic memory. If all conditions are satisfied, the production fires and the actions modify those memories or act on the environment.
And goals, which are symbols placed in working memory, are crucial.
They're crucial because they establish context, limiting which productions are even executable at any given moment and restricting the search space.
And they can be designed to learn, linking directly to the problem-solving theme.
Yes, adaptive production systems possess learning components that modify or create new productions. They learn procedures like solving algebra problems by noting and eliminating expressions that are absent from the final result.
So this rule generation process is an application of means-ends analysis to learn procedural knowledge from examples.
It is.
We return to philosophy with propositional attitudes. These are the mental states, belief, desire, intention, that have representational content. They are expressed linguistically as a relation between an agent and an abstract content, often of that clause.
The core philosophical difficulty here is the content problem, or intentionality. What exactly is the content of that clause, and how does the mental state relate to it? The content is what determines how the world is represented in the mind.
What are the main philosophical accounts of this abstract content?
They fall into two rough categories. First, structured propositions. Here, the content is a complex object whose constituents are fine-grained concepts, Phrygian senses, or individuals and properties.
Okay, and the second?
Informational content. This is the most coarse-grained view. It identifies the content simply with the truth conditions themselves, the set of possible worlds in which the sentence is true.
And how do philosophers try to explain the nature of the attitudes themselves, belief and desire?
Three main strategies exist. One is the dispositional rational action view. So belief and desire are correlative dispositions displayed in rational action.
Belief P equals being disposed to act to satisfy desires if P were true.
Right. Two, the information theoretic view, where content is explained by causal dependencies. And three, the linguistic view, where content is explained by the content of sentences stored in a mental language of thought.
We return to the sound system to define prosody and intonation. What is the key distinction between these two elements of speech rhythm?
Prosody refers to the rhythm so, the grouping and relative prominence of speech elements organized hierarchically. Syllable, foot, word, intonation, phrase.
And intonation.
Intonation refers to the phrase level melody, the pitch contour, or F0, which is used primarily to mark pragmatic force and align with the most prominent elements of that prosodic structure.
These structures are codified using standard systems.
Yes. The Tobai standard for English codifies intonation using basic tonal elements L, H aligned with pitch accents, which mark stress, and boundary tones, which mark phrase edges.
And prominence matters physically.
Oh, yes. Elements in prominent positions are more fully articulated. They occupy an expanded acoustic space.
Why is this structure crucial for communication?
Well, prosodic structure within the word aids lexical access. Prosodic structure above the word reflects syntax and discourse, impacting parsing and operator scope.
And the intonation contours themselves function as independent pragmatic morphemes.
They do. They signal the utterance's relationship to the mutual beliefs of the speakers. For instance, an H accent may mark an intended addition or correction to the shared context.
Following up on that, let's explore the cognitive challenges, prosody and intonation, processing issues. How does this structure help listeners parse the continuous speech stream?
This is the problem of segmentation. Prosody helps with segmentation, but this mechanism is language-specific.
English uses stress-based segmentation, French uses syllable-based segmentation, Japanese uses mora-based segmentation.
Correct. The brain uses the rhythm of the native language to figure out where word boundaries likely fall.
Does prosody then help activate the lexicon once the word is segmented?
In tone or pitch accent languages, absolutely. But surprisingly, in English, stress cues often do not constrain lexical activation very strictly.
Homophones that differ only in stress, like the verb foregoing versus the adjective foregoing, often activate simultaneously.
Right, which suggests that the brain might be relying on other factors, like vowel quality differences, rather than stress alone for lexical retrieval in English.
What about syntactic processing? Can prosody determine the grammatical structure of a tricky sentence?
The evidence is mixed. Prosody signals cohesion, and it can lead listeners to prefer a syntactic analysis that is consistent with the prosodic phrasing. But there is little strong evidence that syntactic analysis is directly derived from prosodic cues. Prosodic structure encodes prosodic relationships, not fundamentally syntactic ones.
The most robust role for prosody seems to be in discourse.
That's where prosodic salience is crucial. Speakers accent semantically central words. And crucially, listeners process information most efficiently when new information is accented and old information is de-accented.
And this de-accentuation actively reflects the speaker's assumption that the word is already integrated into the existing discourse model.
Exactly, ensuring the listener focuses on the novel content.
We return to philosophy to address the scientific status of psychoanalysis. It remains one of the most controversial topics in cognitive science.
The core conflict lies in the objectivity and testability of Freud's original claims, given the diversity of schools that followed him. The debate is really split between brutal scientific critique and philosophical defenses based on the nature of the mind.
The scientific critiques often start with falsifiability.
Karl Popper famously branded psychoanalysis a pseudoscience because it failed the test of falsifiability. Its theories were often immune to counter-evidence. Adolf Grünbaum argued that it relies on causally weak claims and that its therapeutic effects might be based more on suggestive power than objective insight into the unconscious.
But the philosophical defense attempts to reposition it as a non-causal interpretive science.
This view, influenced by philosophers like Donald Davidson, sees psychoanalysis as an extension of common sense folk psychology. It just replaces the belief-desire schema with wish and fantasy.
And Davidson's anomalous monism allows psychoanalysis to search for meaningful connections and interpretations while remaining causally consistent with physicalism, without needing strict psychological laws.
Right.
However, the core philosophical difficulty, regardless of this defense, remains.
That difficulty is establishing the intelligibility of truly unconscious mental states and non-propositional mental content. If the mind operates computationally using propositional attitudes, how can we account for deeply repressed content that is not linguistic or propositional?
And success in integrating psychoanalysis into cognitive science hinges precisely on the latter's ability to model these higher-level, yet often murky, non-propositional attitudes computationally.
That's the challenge.
To understand the contemporary conflict, we must grasp Freud's original foundational claims, starting with his definition of the dream. Dreams and symptoms are fundamentally wish fulfillments.
Freud claimed that a desire is pacified by an experience or belief-like representation of satisfaction like dreaming of drinking when you're thirsty via the activation of neural prototypes, which he called the primary process.
And this primary process was hypothesized to be the brain's earliest and most basic coping mechanism for tension reduction.
Yes.
These complex wish fulfillments were traced back to specific infantile origins.
They're traced back to early childhood interactions, especially centered around the mouth, genitals, and anus, the so-called erogenous zones. These interactions fuel complex, often conflicting, desires to harm or displace parents as rivals and to protect them as caretakers.
When these desires clash, the mind uses repression and symbolism.
Conflicting desires are repressed, rendered unconscious, and can only enter consciousness or action in symbolic form. This symbolism accounts for the hidden significance of symptoms or everyday actions.
The famous example being sublimation, symbolizing taboo incestuous desires as something publicly acceptable, like plowing Mother Earth. This internal conflict also results in the structural formation of the self-regulating parts of the psyche, the ego and superego.
Self-control is achieved by forming fantasy images derived from the parents. The punitive superego forms from interjecting these parental images along with infantile aggression. The ego forms from identifying with parents in their role as agents and satisfiers.
And Freud also applied this structure to group dynamics,
arguing that group identification involves interjecting a common leader or projecting destructive motives onto a common external object, generating the good us bad them dichotomy.
Finally, we must acknowledge Melanie Klein, who dramatically revised the focus after Freud.
Klein inaugurated the object relations approach, focusing on the child's relation to fantasy objects rather than just drives. She introduced projective identification, projecting unwanted aspects of the self onto others during the paranoid schizoid position, which is a fragmented state of self and objects.
And this terrifying fragmented state later yields to the depressive position.
Yes, when the child unifies its images, fearing harm to the now complex and integrated object.
Here's where it gets really interesting. We've just covered an immense range of ideas, from the physics of sound production to the structural architecture of the human brain and the logical foundations of belief.
And if we connect this to the bigger picture, two critical recurring themes emerge across all these seemingly disparate disciplines, uniting the O's and P's.
The first, and perhaps most surprising theme, is the power of the innate blueprint.
Absolutely. The mind begins with far more structure than classical empiricism ever imagined. We saw this in the linguistic domain, where the poverty of the stimulus argument demands innate grammar constraints.
And while parameter setting requires the child to merely select from a finite, predetermined set of options.
In the body, the phantom limb phenomenon confirms a preformed innate body schema independent of physical presence. And perceptual development shows infants are born ready to anticipate events and unify sensory input.
So experience acts as a powerful selector and pruner, not a blank slate filler. And the second theme is the ongoing computational challenge of moving from physical determination to subjective explanation.
Disciplines like AI, so pattern recognition and planning and philosophy, with physicalism and probability, they all struggle with the tension between modeling observable behavior using clear mechanical systems like production systems, while explaining underlying irreducible properties.
This is the struggle to reconcile the determination of the physical world mind-body supervenience with the philosophical failure to explain why subjective experience, like the agony of pain or the consciousness that functionalism makes irreducible, emerges in the first place.
It's a huge problem.
So what does this all mean for the big picture? The fact that a physical entity, the brain, can be analyzed using seemingly contradictory modeling approaches.
Like a constraint-based optimization system like Optimality Theory in language versus a purely causal input-output system like functionalism in philosophy.
Right. It raises a fundamental provocative question. Is the human mind a fundamentally unified computational system operating under a single set of laws, or is it an ad hoc collection of highly specialized domain-specific modules, each optimized by evolution for its own narrow function?
Something to mull over until our next deep dive.
We hope we've given you the mental map you needed to navigate this dense landscape of cognitive science.
Thank you for joining us today.
Until next time.